Hello everyone and welcome to Module 2. We'll be talking about Markov modeling techniques. Oh, and thanks for joining, John. I appreciate that.
Hi,
Hey.
nice to meet you again, or see you.
So, yeah, exciting stuff. All right, so before I get started, any questions, anything you wanted to bring up, or should we go ahead and talk about Markov?
Oh, I think we're in a pretty good spot right now. I figured out the stuff I was struggling with earlier this week,
Right.
and felt pretty good about that. Definitely learning a lot, so very cool, very
Yeah,
cool.
yeah. It was great
Um,
work, by the way. You did a good job on that, so
Thanks,
appreciate that.
appreciate it. Saw your feedback, and I will update my APA practice.
Yeah,
I
yeah,
didn't
yeah.
realize that it actually shifted, so and I never thought running head made any sense anyway. So we'll,
Long ago it made sense. Back in the day of printing stuff out and typing them, it made sense because if you had a stack of, you know, three different manuscripts and you dropped them on the floor, that's where that comes to play, right?
gotcha,
So, no,
gotcha.
some of us are old enough to remember such days and others unfortunately aren't. So anyway, back on
All right,
topic.
cool.
So Markov modeling, fancy name, pretty simple thing. The point of this module is obviously to talk about Markov modeling and why you use it and why does it kind of work and kind of how do you do it in a programmatic way and then what do the results mean. So before we can do that, we have to rewind, and this is old hat, I'm sure, people, but sometimes we forget things, right? So revisiting matrix multiplication, right? So exciting stuff way back when. So the basic formula, if you recall, if you're populating a given cell, let's see if I can get a little pointer here, right? As soon as I remember how to do it. There we go. So if we're populating a given cell like this cell, it goes by multiplying this times this and then this times this and summing up the result, right? So that's how this works, right? So that's where the libraries are making it very easy for us these days. You can basically define your matrix. You can make it look like a matrix and then show how to do the matrix multiplication. So to get to that in a more real way, if this is going to actually work for me. Not going to do it, are you? All right, so we'll do it the slower way. Right, run. Matrix math. All right, good stuff. Not terribly exciting, but it's always a good idea to review just to make sure we're all on the same page. So you start off getting NumPy in because you know it's what's actually going to do the magic. And then just to show that I'm indeed doing it the right way, I did the math and a print statement to show that it looks right. And then we have two matrices, and then we define matrix, or we can display matrix A, we can display matrix B, and then it's as simple as C equals A times B. So a whole lot easier than it was in the days when the dinosaurs roamed the world and I learned this stuff, right? So pretty cool, pretty simple, and it's something that's pretty common. Matrix math is a pervasive technology, deep learning. Big use of such things, right? So you don't necessarily do it yourself unless you're at a really low level, but it's there. So we talked about that. And whenever you're talking about multiplying two matrices together, raising them to a power, it's the same basic thing. You just chain it together. So if you wanted to do a matrix raised to the third power, it's just A times A times A, right? So it's that simple. We talked about matrices, and the reason that's important is because you can use a matrix to represent the way that a system can transition from state to state. So the diagram on the left is a state transition diagram. Basically it has four states, and then there's a probability of transitioning from one state to another, including loops to go back to themselves. So you can go from the state you're in, which in this case it's about kind of the whole pizza sort of scenario of you're waiting in line to get pizza. So you'll wait for a certain amount of time, and then there's at some point after a certain number of iterations, you're going to give up and you're going to balk basically and get out of line and go somewhere else. assuming you have it paid first, right? So that's where a fast food restaurant sometimes can get you. But anyway, so you wait in line, you get up to the line, you order your food. So there's a 30% chance that you're going to get up and actually order your food. 50% you're going to stay in line, and then there's a 2% chance that you're going to leave, right? So that's or 20%. So that's basically how you do these. The outbound arcs, and also which are corresponding over here to rows, the sum of those all need to add up to 1, right? So the probability is equal to 1 that given a current state you transition to some other state or stay in the same state. The probability of that has to be 1. And you're representing the transitions that leave a particular state. So this is the state I'm in, and here's how I'm going to go out of the state, even if it's back to myself, as rows in your matrix. And the destinations are the columns, right? So that's the way we represent it, and it's really that simple. So you basically can construct essentially a matrix that describes the behavior over time, and this is all about time. That's where the key concept is. You're essentially modeling time series analysis is where you use this stuff. So the point of it, we'll talk about why you would do it, or I guess we'll do that on the next slide, so I need to look ahead. So why bother, right? So what's the point? And the reality is that sometimes you can do this to do some predictions, and also be able to determine, based upon either observation, you can actually calculate these sort of things, right? So you have a camera sitting there watching the restaurant, maybe 2 or 3 cameras, whatever it might be, and you can basically could count the number of people that are coming in, count how long they wait in line, figure out after how many minutes each one of them leaves, and so on, and actually construct the matrix. Then you could potentially figure out things to make changes to those matrix, right, to the matrices, so that you can modify the outcomes. That's the basic idea. And the key thing is that raising a matrix to a power is the same as that number of time periods elapsing, right? So that's kind of the whole point. So again, back to try to make this a bit more engaging. Let's see, this is the pizza example. And
Dr. Dennis?
yes.
I do have a question. I was watching the Matrix portion of the multimedia presentation in Module 2 last night.
Yeah.
And at, it looks like 4:29, 4 minutes and 29 seconds, they show squaring the matrix, and the numbers that result from that squaring of the matrix don't look like squared numbers. It's like 0.5 in the top left corner goes to 0.27. So I was
Okay.
at that point I just went to bed. But
yeah, well, actually, well, we'll see, right? Because here it is.
Yeah.
This is the 0.27 you saw. The behavior, you've got a lot of columns, right? So that's what's going to potentially drive it down. So we start off, obviously, you pull in NumPy because it's cool stuff, right? And it makes it really easy and it's really fast. You define your matrix based upon the characteristics of that sort of situation. So that is a representation of that state transition. And then you basically are setting P equal to it, right? So this is P is that, and we can see that it is set up that way. Whenever you square it, it will go down to 0.27, right? And that's because you're calculating this destination by doing a whole bunch of rows and columns adding up together, right? I mean, if we could do it by hand, but I would trust if another way you can to prove it is right, just do a simple multiplication, P times P. It's the same thing, right? It's just a different representation. So yeah, it's not, it wouldn't be 25 if you thought it would be 25. It's a more complex thing, right? Because you got to go.
I just remembered that yeah, that's right. Okay.
Yeah. Hence the one that seems like, oh, what is he wasted my time talking about this for, right? Because frankly, we don't do this day on day out, right? So we forget it, right? So it's this the process of the
diagonally. Yeah, I remember now.
All that good stuff. Yeah.
I'll refresh on that.
Oh yeah. Well, yeah, and you don't. That's what NumPy's for, right? So,
right. Yeah.
But it is important to understand that behavior because that's really quite interesting. That means that the behaviors over time are changing, and the probabilities are changing, so that as you're in line longer, your willingness to stay in line will change, right? So it may go up, may go down, probably goes down at least for me, because I'm an impatient person.
Right.
But that's kind of the whole point of this thing, is to kind of be able to model it. So going from, I mean, state transition diagrams are, I've done these for years, right? Of, uh, of basically defining states and transitions between them. A lot of times you don't include the probability if you're just doing a simple state transition diagram, right? But adding that probability and turning this into a mathematical graph, and then taking that mathematical graph and turning it into a matrix, and then being able to do matrix manipulation to it, and where each of those multiplications or power, or basically each one of the multiplications is essentially the event of a time period
Wow.
passing. That's really cool, right?
That's really cool. That's really cool.
So and very useful. It's also, I didn't dig into it as much as I might have liked to, because it could get hairy quick. But you can combine Monte Carlo with Markov processes, right? So that kind of seemed pretty cool. I might take another look at it and see, but you don't ever want to bite off more than you can do, right? So that's we want to be successful here, not try to boil the ocean. So taking a look at it from an R perspective, and you can hopefully the screen is big enough that you can see it. I can make it a little bigger.
Yep. That's pretty good.
So you need to install the package XPM or XEXPM to do the actual magic. But it's the same sort of thing, basically. You can combine these things together, make sure that the library comes in, and we wait a little bit, and hopefully my environment's not hosed up. And then you can, the whole point of pulling in that library is to get this funky function that they've overloaded, right? And then the same basic thing. So again, it's a similar sort of experience, and this is all about creating. Probably should print out P there, shouldn't I? Because that'd be kind of useful. Right, so creating a matrix by doing the R-bind to combine together the vectors essentially to create a matrix, and then using that library to do this magic stuff to do the actual raising it to the third power. So pretty cool, pretty straightforward, and also kind of some compelling sort of stuff there as well.
Cool.
Yeah, and then it gets into, we can go ahead and try SAS, our favorite language. And again, I'm sort of using SAS. So SAS has a IML, which stands for Interactive Matrix Language proc that you can invoke, and it's the same basic scenario, right? So, and I'll go ahead and just so that you can show I'm actually nothing up my sleeve. Rerun it. So there we go. So pretty cool, and then it produces the output down here as well. And with any luck, they're all the same numbers, right? So 0.26, 319, and 4119, and 436. So yeah, same result. And these may be slightly different, but 262. What did I do here? Different matrix? Yeah, different matrix. So yeah. 2 or 3 different examples in there that I'm kind of commingling together. So the one was the pizza story sort of thing, and then this is a slightly different one. And then talking, I don't think I did this one yet. Same basic thing, right? So I think that may be the one I just did. Yep. So what's the difference here? Why did it let me open it twice? It's interesting. Should have taken me to it, I would have thought. Anyway, so moving over to interpreting, which is kind of where the magic is. And we've talked about it is over units of time. And the example they give is actually fairly good of doing, shouldn't need to install, I can just bind to it, of doing what if analysis, right? So imagine you're a manager or whatever at a marketing part of a credit card company, and you want to do things that maximize people utilizing your services. But you want to do so without having them go into default, right? So it's you would like them to be probably just at the edge of their limit, but always be able to make make their payment, which is kind of a dark way of thinking about it. But so they give you the sort of the matrix of what the probabilities are, and this is, I should have done this one first because this is kind of the one that we're tying together. And then so basically it shows you again from the state you're in to the state you're going to. So you go from a zero balance to a default should never happen. Non-zero, 10% chance. If you're in default, you're probably going to stay in default. But there is a 2% chance that you might actually, or 20% chance that you might come back out of it, right, to having a balance. Similar thing, you basically create the vectors, then you bind them into the matrices. There's two different matrices here, and we'll look at each one of them. One is kind of the one that is the default that they've given us, and that's what we see here. And you run through it, and what happens after 36 months. So this is a probability based on state transitions per month. We do it for 36 months simply by raising it to the 36th power and take a look at the probabilities of where things are going to be. And they've reached some sort of stasis, right, is what it looks like. So pretty interesting. And that, sadly, that is life. And it seems to be modeling pretty closely. You reach some sort of level with credit cards typically, unless you're very diligent. So then the scenario is, well, what if, right? So what if they do something where they can change the probabilities of things occurring and making some minor changes to the things, and then they can basically model that by doing the same sort of approach and getting back the results of showing it where things are based upon that thing. So it's basically shifting it somewhat from where the ending state is likely to end up after 36 months. So pretty cool. Not exactly the same values, but close enough that they might as well be, right? So pretty interesting. But that's a product that you'll have with a matrix manipulation. Is if you multiply it times itself enough times, you'll get close to, I don't know where it'll go. Probably it'll stabilize most likely, or very small isolation or oscillation. So that's that. And I think with that, we've talked about Markov. So I'll pause a little bit. Questions, commentary? Is it making sense?
It is. It really is. It's really cool how you can take, the facts that you've observed and then map them mathematically into probabilities of state changes.
Yep.
The thing that I've done before as part of the natural language processing we were studying in a prior class was really interesting. A third order Markov chain in the corpus would look at the probabilities of, the lazy brown. Looking back, you'll find that dog usually follows that, right? So then you go to lazy brown dog jumped, so that third order Markov chain will produce automatically from a corpus with probabilistic selection sentences that almost sound like a human created them.
Yeah.
And that is just fascinating to me. So I'm really excited about this subject. And when you think about the power of taking the Monte Carlo approach to building those probabilities and assigning them to the state changes, it gets to be really interesting. There's a Reddit group, I forget what it's called, but they actually have articles built by Markov chains.
Right.
And a lot of them sound like a person typed them. It's really cool.
Yeah.
So,
and there's also, I've seen, I'm covering the material as it's presented in the course, but I've also observed there's variations on this theme where you multiply an initial state times a probabilistic transition diagram to determine the next likely state, right? So it's you basically put somebody into one of those states with a 1 and everything else is 0. Multiply that times the probability matrix to essentially model it going from one state to another.
So you're always looking for the state you're in forward.
Right. Yep. So there's lots of variations on this, and some of them, it's oddly enough, a lot of the literature doesn't seem to talk about the matrix multiplication sort of approach. They'll actually do the math themselves. So it looks like they're actually basically doing matrix multiplication iteratively, which is interesting. But anyway, I digress. Deliverable 2. So you guessed it. You apply Markov modeling to solve a problem. And the rubric is the source of truth. So that is what I grade by. I will stick to it explicitly. So interestingly enough, the rubric doesn't really address APA, right? And I wouldn't have beat you up much anyway because your APA errors were minimal compared to
I'll fix
a
it.
lot. But it doesn't really say that as a rubric criteria. So
Yeah, that's sort of one of those meta expectations I think that we should just, expect
yeah,
to adhere to.
yep. So yeah, it's not all that hard, but it's amazing. I teach doctoral level courses as well, and a lot of the doctoral students, they don't get it. They don't get that it's a thing. That's what they don't get.
Right.
That it is beyond just parenthetical citation. That it is a very exhaustive sort of thing, even including if you get down into the weeds of how you present numerical results of analysis, right? So anyway,
Yeah.
it's
I've got the sixth edition book. I'll have to get the seventh just because I like, seeing how to do those things.
yeah.
I think it's really important to be able to publish things in a way that other people are familiar with and can interpret easily.
Yep. Yep.
That to me is the whole point of it.
Yeah. The standardization's nice. You don't have to. It's just jarring if you're reading something that's not quite right. It distracts from the material, right? You're looking at what is this
Exactly.
format, right? Versus what are
Yep.
they having to say. So
Yep.
anyway, again, I digress. So your bank's offering home equity loans. You've got some data, including basically there's 5 states. So current, late, collections, paid off, or default. Kind of sounds a little familiar to some of the other things, right? So here's your basic transitions. So if you're in the current, 70% chance you're going to stay in that same state. So loop back to yourself, 20% that you're going to be late, 10% that you're going to pay everything off, and so on. I'm not going to drain that. So that's basically how you construct your matrix.
Yeah.
I would probably draw a picture too. That's just me though. I like pictures.
Mm-hmm.
And I don't know that it spells it out, but it helps you visualize it and also double check yourself that everything adds up to 1. So easy to do and easy to fat finger it, but it's not a huge deal otherwise, but still. So your manager, Paul Freeze, is interested in the expected state of a loan. You're to determine it over basically the 5 states over 36 months. Really sounds familiar, doesn't it?
Yeah.
In addition, you're going to basically apply Markov processes to determine basically where they end up at, and talk specifically about how it can be used, what are the advantages and benefits, and if you want to go crazy, what are the disadvantages, right? And then so here's your detailed instructions, as always, source code, Word document that includes screenshots of the output, and then again a memo, which is kind of interesting because APA and memos don't really go together, but okay, we'll do that. Yeah, anyway. Yeah. So present the final state matrix indicating the probabilities, and then probably talk about it, right? So provide an interpretation of that state, and then where can it be applied and what are the advantages and benefits. So pretty simple one, really. Not as hard as some stuff we do. And then what do you turn in? Same thing you always turn in. Word document that is your memo. You can combine those two as you suggested. It's a great idea. I think it was you that suggested that. You don't need to be 2 different documents. And the source code of the various languages you pick. Not to bias anyone, but a whole lot easier in R and Python than in SAS. But that's just my opinion, and they're prettier too. SAS just is so like, I don't know, COBOL or RPG or something. It's like,
Yep.
Anyway, hard to type. You kind of
Yeah.
It's hard to type with one hand because you're holding your nose with the other one, right? So anyway, the rubric. Source code, this also is pretty similar. Is there source code that is well written in multiple languages? So that would be 2 languages. And then screenshots that are clear and well planned, that shows basically add value to the experience. Description of the transition matrix, a clear and thorough presentation of the final state, indicating the probabilities after 36 months. So that's probably just a nice little table, and then interpretation of said table. So what's it mean, and then application where you could use this. And spoiler, pretty much anywhere where there's time series analysis that has probabilistic transitions, right? So anyway, my take on it. Like I said, to me, it's a really cool, but it's a really simple thing, and but yet there is some compelling and interesting things when you talk about. It sounds like basically n-gram application with Markov chains. That's kind of cool. It'd be cool to be able to do stuff like that in some of these courses, but we kind of have to stick to the script. So anyway, and with that, I'll go ahead and pause again for questions, commentaries, discussion.
That's all really clear. Appreciate the walkthrough. And, what I'm thinking about is, applications of this, because I remember back when I was learning, to code in C 30 years ago, we did an elevator simulation program, right, for, estimating the amount of elevators you'd need given a certain number of people and size of the building and everything.
Yep.
And this would be something you could apply to that more effectively than what we did.
Well,
so
that actually,
that's pretty...
that kind of sounds a little bit like maybe the Monte Carlo and Markov, right? Because you've got a probability distribution of what floor somebody might go to. Likely not everybody goes to the same floor.
Right.
There's also, well, it gets really complicated because there's probably flow patterns within who goes where when. But yeah, that's definitely, and a lot of your simulation packages will include the Markov sort of implementation. You don't see a matrix, right? But it's there. It's what they're doing underneath the covers, especially when you're dealing with a discrete event simulation, which is kind of cool, right? But it's also, the math can't be easier, especially with GPUs, right? I mean, that's just straightforward.
It's magic. We can literally do things we just couldn't do, 40 years ago. These computers are so fast and powerful.
Well, it's not even 40, 30 or so. I mean, way back in grad school, it was a simulator as well for an elevator, but it was a 3D sort of thing. Very simplistic. You push a button, it goes to a floor, but it was in a 3D wireframe and saw that. Now people would like, where's the shading and the gradients and the diffusion of the light sources, right? No, I was happy to have a box with another box that moved up and down in it, right?
Yeah, kids these days are spoiled.
Definitely so.
Yep.
So appreciate the conversation as always.
Likewise.
And for those of you who it's one person, Eric, I think, as you're watching this, if you have questions, comments, let me know. That's what I'm here for. I want you guys to succeed. I want you to do well and learn something, because this is cool stuff, even if the title of the course is kind of scary, right? So not all that advanced in a lot of ways, because when I saw the title, I was kind of like, well, sure, I'll teach it, but I'm not the stats guy, right? I mean, I try not to be one anyway.
You've got the chops for this, no doubt. But these are bite-sized chunks too, and understanding them fundamentally and how they work is, they're like Legos. They're like every other tool in our toolbox.
Yep. Yeah, it's a good course. I like the material that it's covering, and it does it in a nice way that ties it all together. It's pretty impressive.
Awesome.
It'd be cool to tie it in with some of the stuff you do later on, like whenever you take like the big data course, doing something with the matrix manipulation or whatever in a Spark cluster would be kind of cool. Be probably hard, but be cool. Anyway, so I digress again. So again, if you have questions, let me know. Thanks again for joining. I appreciate it. And stay safe. We'll talk again on Monday, right?
Perfect. We'll see you then.
Sounds good. All right. Goodbye.
Good night. Bye-bye.